Hi, everyone. Thanks for inviting me to talk at this session. I'm really excited to be here. So here we have dots representing locations where we've actually recovered methane hydrate all over the planet. The stars are special spots that I've personally been to out on the ships recovering hydrate or collecting well logs, which is my specialty. And you can see lots of things about this. For one, we find a lot of hydrate hugging continental margins because what causes hydrate to be there is organic matter, and it's biotic in origin. Almost all hydrates we do have on planet Earth are biotic, except for just a few years ago, there was this paper published about this hydrate off of Svalbard that we think is abiotic in origin. So that's the little black swan we just heard about in Australia in the last session. But basically, if you haven't seen any hydrate, I put in this video that I love to show all over the world. Here you're looking at hydrate burning. Hydrate is really concentrated methane surrounded by a water lattice. It looks like frozen ice, it looks like snow, and people are interested in it economically as a potential form of natural gas, and also maybe a really large component of the Earth's carbon cycle because it may contain 15 to 40% of Earth's carbon. So that's why I study methane hydrate. I'm really interested in how much carbon there is in hydrates. But I also want to come out to you guys starting in this talk because I'm not a biologist or a microbiologist or even a chemist. I'm a petrophysicist and geophysicist, and what that means is I go out on ships. I spend a lot of time looking at this seismic data you see in the background. Here we have the seafloor and all the layers underneath the seafloor of sediments, and I try to figure out where we can drill to find gas hydrate and understand the system. And that's a really rewarding part of what I do because if I'm lucky and all of the stars align in funding, I get to go out and actually drill and figure out if the ideas I have are working out and making sense. So that's a really rewarding part of my work. And I really love thinking about gas hydrate systems in the subsurface. I want to know what the dimensions are, what the features are, what kind of complex systems are interacting, and I actually find that microbes are a huge part of gas hydrate systems on Earth. Before I get to that, I just wanted to do a couple of definitions because I know we have a really broad session. We find gas hydrates in marine sediments all over the world where we have low temperatures and high pressures. Here you're looking at the sea surface down to the seafloor and then into sediments. And you're looking at the hydrothermal, geothermal gradient. So the ocean is cooling all the way down to the seafloor and then starting to warm up in the sediments. And if we can put the clathrate or hydrate stability boundary on top of that, you can see that we start getting clathrates or hydrates stable at about 300 to 600 meters, depending on the temperature of the ocean and that location. And then they're stable down to the seafloor at this location, and then they become unstable in the sediments because the geothermal gradient warms up to where it's too hot for hydrates to be stable. On planet Earth, however, we don't really find hydrate in the ocean anywhere. We don't really find much methane in the ocean. All the methane is nearly dissolved because the ocean is undersaturated in methane. I can imagine really exciting planets out there where you would have hydrate forming here and then floating up in the ocean system, icebergs of natural gas hydrate. We don't see that because of the ocean being undersaturated in methane. So we really see hydrate just kind of forming in this zone here from the seafloor down to where it becomes too warm in the sediments. Another way to think about that, if you don't like the stability diagram, is like, here's you, and you're like hanging out on the ocean, at the beach, and maybe you have a margarita. And over here you have the continental shelf. You don't have any hydrate stable there, but then as you move down on the continental slope, the water column gets thick enough, and so the pressure is high enough that you have hydrate stable in the sediments. And then the hydrate stability zone thickens as you move out of the deeper and deeper ocean columns. However, when I show these diagrams and when people first start thinking about hydrate stability, I think it gives you this wrong perception that hydrate is really homogeneous in the subseafloor system, and that is beyond the truth. In fact, we find hydrate systems to be completely heterogeneous in diverse types and different types of sediments, and that microbes are contributing differently in these different systems. So here you're seeing a really new, in fact, right now not published. I just communicated with the lead author of this paper that's going to be coming out in Reviews of Geophysics, and I think you guys might be interested in it. She has identified 5 different types of hydrate systems in the subsurface. There may be even more. One of them is this sort of classic system where you have like an anticlinal system that brings gas up from deep and thermogenic gas, and it moves through the hydrate system and maybe creates these sort of fractures here, and then you actually have gas moving into the ocean. That's like the kind of classic one that's really easy for us to identify, and in fact we know the most about that system. But there are so many other systems that we find in the subsurface when we actually go out to drill. Another one that's kind of like more petroleum-y and more typical for like a kind of petroleum system, where you have gas moving again from below, but this time in a more permeable sedimentary layer, like a sand-rich system, and then you have gas below and hydrate above. And then we have this like kind of confounding system that we've just started to find over the last decade, where we found hydrate at high concentrations in these thin sands that were far removed from the base of the hydrate stability zone. And like, how did the hydrate even get there? That was a very confusing thing for us. I'd like to talk about a model that I put together with co-author Alberto Malinverno, Lamont Doherty. That shows how you can get really high saturations of hydrate and sands. And I was just talking to Megan, Elle and Madden yesterday about hydrates on Mars, and like there's definitely coarse-grained systems there as well, so you could have this kind of system happening on other planets. So here we have sand at the top, and we have mud. You can just think of this as mud and all the gray. And we have a couple of different things happening. First, we have the solubility you have to reach, so the amount of dissolved methane you have to get free gas out of the system in this dashed line, and then the excess amount you have to make in fine-grained sediments, because the pores are super tiny. So you actually have to make more methane to get methane to come out of solution and become free gas. So there's this difference here. And then on top of this, I've drawn like a potential dissolved methane profile. Well, in this system, we have achieved enough methane down here for the sand, but we don't have any sand. So over here, we have literally no hydrate. No hydrate yet, just dissolved methane. And then if we move the sand down over time due to sedimentation and compaction, the sand would eventually reach that higher dissolved methane concentration. And bang, you have hydrate. And forming the hydrate actually lowers the dissolved methane concentration, and so that you have higher dissolved methane concentrations around it. So you actually end up with a diffusive flux of methane coming from fine-grained or muddy sediments into the sand system. And it's a continuous diffusive flux, and if you've got microbes around that, you're continuing to create more and more methane, and more methane goes into the sand, creating more and more hydrate, and you can get really high hydrate saturations without any amount of methane hydrate actually forming in the fine-grained sediments. And then you can also have even more developed systems where you may have even more methane being generated as you move the system down. And then you may see hydrate also forming in the fine-grained mud surrounding it, and then this like hydrate-free zone, and then more hydrate in the sand, and then another hydrate-free zone. So you can get these really heterogeneous distributions just based on simple things like differences in solubility between marine muds and sands. Okay, so I hit on a couple of these systems. Another really interesting system that we've identified in the subsurface is this fractured system over here. These are methane hydrates forming in fractures in marine muds. They're near vertical. They are interestingly forming in layers. So unlike this system over here, which makes sense, you've got gas coming up and things are fracturing and methane's coming everywhere. Why was the hydrate in fractures here? And then why is it forming in these really large layers? I'm not going to talk about the fracture formation here, but I'm happy to chat with other people about that. But I am going to talk about those really large layers of hydrate in marine mud. Okay, so this is some work I did with Jess Hillman. She's now at JNS Science in New Zealand. She did all this mapping of a seismic section that we had in the Gulf of Mexico. And we tied well-logged data that I have in these two sites, and sorry, that's a little sliced off there at the top. And we were able to identify not just one layer, but 3 layers where gas hydrate appeared to be in fractures extending kilometers. So here's a kilometer here, you guys can see. So this is like 8 kilometers of gas hydrate in layers over this basin. So that was really interesting. Like, why is the hydrate forming that way? You can also notice when you look at this that it almost looks like there's a cycle. Like, ooh, hydrate here, no hydrate in this white spot. Hydrate here, no hydrate again. And so this cyclicity, I was like chatting with some people at a meeting, and they were like, I bet that's related to glacial cycles. And so organic matter deposition can be higher or lower during different periods of time, and also glacial cycles really affect that organic matter distribution. So we looked at sea level high stands or low stands. Another way you can think about that is just low sea level and high sea level. So when sea level is low, you actually get more organic matter far out into that sort of deep water system. I'm sorry, I showed you the map over here. This is really deep. We're at like 2,000 meters of water. So to get more organic matter out there, we want to have sea level low. And so when sea level is low, we get higher organic matter distribution. So we took the data that we had from the well logs there. We took an industry well where we had some biostrat information that gave us some ideas about the approximate age of the sediments, and we were able to fit a model where we created the amount of gas hydrate we thought should be in those layers based on the sea level high stands and low stands. And we think we were able to match things pretty well to what actual data we measured in the hole. So this is our resistivity logs, and they can give us an idea of where we have natural gas hydrate. And you can see we found hydrate here in the pink, hydrate here in the pink, and here's what our model says we should have. And so this bottom part from about 250 to 400 is matching really well. We did that in a neighboring well where we have a different biostrat age, and again, it was matching really, really well. So those cycles that we were seeing before, we now have this hypothesis that they're related to glacial cycles and are influenced by the amount of organic matter that's deposited. Okay, so in summary, methane clathrate hydrate systems on Earth. Hydrate below the seafloor is really complex system, and it's heterogeneous in distribution, and I think that microbes play a huge role in subseafloor hydrate systems. So thank you very much. I just wanted to acknowledge all of my funding here, and also here's my contact. I'm happy to chat with anyone about how we find hydrates in subseafloor systems.
To the microphone. Okay, good. We have people coming up, and there's lots of seats up here too, but if anybody has questions.
If nobody has a quick question, I'd just like to say, we just heard that there maybe is a lot of methane on Mars, and the systems that would be really similar to that are these like belching systems. Here we have gas coming out, and also over here in permafrost systems where gas is coming out. But that doesn't mean that we don't have all these other complex systems happening on Mars as well. On Earth as well, these systems are the easiest to detect. And so we're just sort of picking up, I think, the complexity of what could be on a place like Mars. Oh, hi.
So I do have a question, although this is a bit tall for me. I just wondered whether you've done any work looking at the isotopic composition of the methane in the different regions, and whether you've seen any difference in the isotopic composition depending on the type of methane clathrate that you've got there.
Okay, so yes, we have geochemists that work in hydrates that study a lot about isotopic composition. As I mentioned at the beginning, like nearly everything we think is biotic on Earth, but we also have like a lot of microbial and thermogenic methane that's forming hydrates. In fact, though, places where we think we should be finding hydrate that's thermogenic, like this one, where we seem to have gas coming from deep and below, we are finding over and over again that those tend to be more microbial, and so we think those may be reworked microbial systems where the thermogenic gas is coming up from below, and then microbes are then altering that gas. And that's a really new idea, but we keep finding it over and over again.
Maybe a question. Time for one more quick question.
Way in the back. So if this is related to microbes and you've got this kind of sporadic distribution, how do you explain that interaction? I mean, aren't microbes going to be a little more ubiquitous?
Yeah, I think it's really the coupling between where the microbes are living, how they're generating methane, and then the geologic system that's there. So like I was showing where we were getting large amounts of hydrate in the sand and maybe not in the muds, well, the organic matter is in the mud, so It's moving somehow, and the microbes are making methane somehow, but it's concentrating then in the sand. So maybe the microbes are living more in the sand, or maybe they're and methane is moving in a dissolved, organic matter is moving dissolved into the sand and creating that hydrate.
Have you looked at any sequence stratigraphy as a predictive model for this?
Oh, that's such a good question. I just wrote a proposal.
I'm a sedimentologist.
I just wrote a proposal to get some more data and cores from the site where we did that modeling to look at glacial cycles involved in microbial methane. And I'm really interested in getting the sediments from there because I would really like to understand the sequence stratigraphy better and also get much better age dating so that we might be able to prove or disprove that hypothesis.
Very good.
Great. Okay, one more round of applause for Ann Cook. Thank you.